Okay. So hi everyone. Let's start our seminar. Welcome to the Minh-Nhat reading seminar, and today we are very happy to have Minh-Nhat Phung, who is currently a PhD student at Texas A&M, Professor Minh-Binh Tran. He is talking about control optimal transport and a Sinkhorn-inspired algorithm for neural differential equations. Please, yeah.
Thank you for your nice introduction. So this is a zone work with my advisor, and we're still submitting to. We are in the revise. We are revising the paper and submitting it um, for for today's talk. The first thing I will want to introduce some of the concept that I actually write here, like what actually is the thing that the neural differential equation, and then I will try to talk about the motivation for the control or and some application, and then to construct the neural differential equation. These are the tools that I use, the optimal transport and the solver like Sinkhorn-inspired algorithm. So let's head to the introduction. So the first thing about the neural ODs, um, I want to introduce the single layer neural networks. So for single layer neural network, we have in neural network, what the important factor in here is this function, sigma function. So the sigma function, in this case, to to simplify other definition, I consider I working on one single the dimension d, so it not get confused with other dimension. And so in here, the function sigma will are component wise. So you can see here, like for every component, we will put only single sigma on every component. And originally, this function sigma we call activation function. So the structure of the single layer neural networks, we have this is one linear, so that's what a linear function, and then we have an activation function. Usually, it is non-linear, and then we might add some more weight in here. So the purpose is that we have some a last function that is nonlinear, and we want it nonlinear because it will improve how the function can approximate a lot of other function. If we only have a linear function here, then no matter what we do here, this function is not linear and it's not well. It cannot approximate other function well. So we do need this sigma is nonlinear, and then in application we usually choose the sigma beforehand and we just fix it. We don't change the sigma, and we have some example where um, this is the most popular one where we use a rectifier. uh, we know it by the name ReLU, or maybe we can like put some polynomial in. So we have RePU, where you have a monomial in here and then you take the max with zero. So these two are more popular. And then we also have in here, for example, ReLUs, they don't have the derivative at zero. So some other activation function, they want kind of a smoothness, so they can put all the activation function in. The idea is that they only need to be nonlinear. Um, and of course, yeah, we can consider different activation function because um, it is better to have like because they can be have differently depends on the model that they want to train on. Yeah, so they consider a lot of activation function. In our work, all of these we only need to they are locally Lipschitz, and they are classified as at a class of neural network. It was named by the name neural approximate identity. I will talk about that definition later. But all of this it is applicable in with our theoretical results. So now we're starting from a single hidden layer neural networks. And now what we do, because we're working on single RD to RD, so now we can use the function to describe like a flow. So we try to put a neural network to approximate kind of the chance between 2 points. And so this will describe a flow. We can consider it as a sequence, and then it moving from xj to xj plus one. And after that, we can like put some time dependent on. We can put a scaling, the time scaling to the difference. Um, and when you see this model, of course, naturally, you can see that if you put this at a time, and then you scale this to zero, and then you have a time continuous model. So this is the neural OD that we want to talk about. So and then after the neural OD, we can actually further make it a little more general. Instead of that, this is a trajectory of 1 point, and then we can make it into a distribution. We can assume that we can move a whole mass, not just 1 point. The continuous model, the time continuous model, transform into a distribution, a transport equation between measures. Um, Actually, when moving from this to this, of course, this is we will write it from this if we write this into weak form, and then we will need some density argument on the test function. We can derive this to this thing. It's a little bit work. One can use a reference textbook, if I remember correctly, from gradient flow. So from Ambrosio, Gigli, and Savre. So they have a book on gradient flow, and it describes how this thing become a characteristic equation for the transport equation in here.
Yeah,
Um,
I have a quick question. So
yes.
basically here you're talking about the formal argument, right? Because you don't need yet any kind of regularity on the
Um,
coefficient. So
yeah, we later on when we try to construct something, of course, we will need some certain regularity. But for
mm,
now, this is just a motivation why we move from a very first single layer neural network
mhm.
to a model that is the transport equation for
Yeah.
between
Then
measures.
then 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 you can just say that you have the ODE, which is exactly the characteristic of this transport equation.
Yes, yes.
Yeah.
Yeah, this is supposed to be the characteristic of this transport equation.
Yeah.
Yes. Yeah, of course, that another another background theory that not that it's not that obvious, but needs some work on that. Um, but it's a classical result, so we can actually find it in some textbook for gradient flow. In here, of course, for a measure, it might have many different forms, but we consider continuous testing. So we put it we define it with a density function, and it will absolute continuous under the Lebesgue measure on RD. Of course, other author will try to also do with different model. In this case, we try to do to absolute continuous under Lebesgue measure. And because it is transport and this is homogeneous transport, you can see the zero here, the homogeneous transport equation. So the total mass of the two density, they have to be equal. They have to be equal. Um, so usually we also say this is the balance transport because the two end have the total same mass. Of course, some other thing that to improve regularity, like as you mentioned, we consider the compacted support and maybe continuous and non-negative. It's just something, but this is that I will try to clarify them further a bit more later in the assumption. But the idea is that we have two density function and we want to transport from one to the other, and the trajectory, the flow control, it defined by these these the parameters. And yeah, of course, this is the motivation that I want to mention. The reason why we go from the decrease setting. So this is a decrease. They move from one point to one point, and now we make a continuous model. Because actually from the idea from in Jan in 2018, and maybe also from paper and root root total in 2017. So they do provide that they do provide algorithm with its model, saying that it actually better compared to just trying to do the discrete setting. One of the reason is that because they actually can use another solver to solve the problem rather than just use the discrete solver. And so one of the advantage when we try to consider this model is that we can have other solver to use here. And so that's why we in here, after we have continuous testing, we can use the Sinkhorn algorithm with the optimal transport. And then we also have Monsieur-Ampere, because Monsieur-Ampere also link with optimal transport, and then we can use the solver. Usually, all the people already working on Monsieur-Ampere a lot, so um, well, we can say that we have the solver, and we can just apply the solver to construct the neural networks that we want to approximate here. Um, Now, for the applications, I only list a little bit here. Uh, the problem that we actually looking we the first thing that we read is in design and review on 2023. So they doing on classification problems. So for classification problems, actually they working on a little bit different. They need the endpoint. The end is a decrease setting. So it's a little bit different, but the equation here, they have same form. So it's one of the motivation when we working on. And for the continuous testing in here, they usually use for normalizing flows, and they use for generative models. So they usually coming from maybe a Gaussian distribution, and then they try to generate a new. They try to come up with a destination where it looks similar. So they apply for generative model. This is just one example. I think a lot of other example might available. Um, but now we're looking back at the model in here. As I mentioned, this is a homogeneous equation, and so this um, this requirement is you must have when you consider this equation. So one thing that we want to do is to remove this limit. We don't want they absolutely must be the same mass. It might be a little bit different, and so we add in a more one more control. This is the mass control, and so we still focus on the neural network on here, but we have the mass control. So the problem is no longer need this requirement. So we can have a little bit more free, more flexible on working on the problem. And what we want to do is that the solution here will approximate maybe a flow also from F to G. This regime I will also say later when we go to the result. Um, Now for why we want to remove this thing is, of course, a lot of object when it's transformed, it not the mass is not preserving. For example, when we look at the paper on cell on 2019. So the cell growing, and then you see over time when the cell grow, you don't want it like stay exactly the same mass. It may grow, or it may shrink, but it will not have the same mass over time. So a lot of objects are also very similar, and they don't want to have the same mass on the model. So this model makes sense in actual application, and others, for example, in well, TZ on in 2018. So he also noticed that a lot of people trying to do the unbalanced transport, and then he also like devised some algorithms with the with the Sinkhorn algorithm to try to solve optimal transport for unbalanced transport in here. They remove this condition, and they make an algorithm for that. We actually try to use some later, some more recent algorithm, so that it might have some better performance for the optimal for the transport. So that about the motivation and why we consider the unbalanced transport in here. Now, uh, for previous approaches and challenges, the thing is, the previous approaches are mostly focused on this thing. So for unbalanced transport here, for the inhomogeneous transport, it's kind of not many people doing the neural transport yet. So it's kind of a blank in this in this case. But in a for balance transport, also from Ballet and Zaza on GMPA, so they use kind of geometric approach. So the idea is that they have two density function, and then they try to cut two density into rectangulars. Usually that means they using the Riemann sum, and then they try to move one rectangular to the other places. So they what they do is they try to move every move. They try only one single rectangular, and they have to cut into a lot of rectangulars. So one thing is that it's highly inefficient, and of course they have to assume that the total mass must be the same to do that task. And so it's also very hard to generalize. Um, it do very kind of intuitive construction, so it's reasonable in a sense, but for it's not yet going. It's still far from anything that optimal in a sense. And then we have another author who working on also on this transport. And one of the problematic thing is that the assumption on the equation is that the vector field here have to be uniformly Lipschitz. Um, but it's very problematic because usually this thing we actually don't know. Um, this is the thing. The vector field is something that we are trying to find. We try to approximate. So given that it must be an assumption, it's kind of hard determine whether we can do anything in here or not. And then uh, yeah, and the argument is also quite simple. They only need to say the the space of neural networks stands in the continuous function, and they have a uniform ellipsis, and then they can make the solution approximate to this to the choose to the exact solution. Although yeah, one thing that we want to avoid is that we have to assume anything on the vector field here, because that the vector field is something that we actually don't know yet. So and then for the unbalanced transport that I mentioned, that the inhomogeneous equation with the mass control, um, the many previous algorithms mostly for discrete setting, and so they don't have algorithm for continuum setting. So we have to um, make the algorithm for the continuum setting. And one problem with unbalanced transport is that the two vector fields in here, it usually not unique, even if they are optimal. Usually you can force this unique if it is optimal, but for unbalanced transport, they are not unique. So the construction you can we have to uh, very specific about the construction to ensure that it actually converts to something. And that's where the task is a little bit hard in here. Um, and then so that the previous genesis and for our result, what we actually achieve, the first thing before we say about the actual result is that the assumption. So as I mentioned before, we try to avoid the strong assumption that is starting from the vector field. Um, for our assumption, we only assume on the two density functions that usually what we are given with. So it makes sense that we can have some assumption on the given. So on the given density. So we usually have convex support, and we do need a convex and C11 boundaries on the support. Um, it has to strictly positive, so it avoid the zero here. Um, we also assume that it is bounded above. And the activation function, as I mentioned earlier, we actually can use a lot of activation function. As I mentioned, like all of these, we can include them in. Um, in in one of the paper on applying in 2024. So the author Bhutan do classify this kind of uh, a lot of these activation function, and when with the correct activation function, usually he said that it can when all the function can draw written in this form, when the activation function can he can form an approximate identity using this form. And so one can see one we see here is that we can make approximate identity using kind of a finite sum with activation function, and this is the structure of a neural network, a single layer neural network um,
Yeah. You
on
mean that F
V
and
equal one.
sorry.
Yes.
Yeah. Yeah. Sorry. You mean that F and G are strictly positive inside the support, right? I mean, uh,
Yes. Actually, we only need to consider within the support.
yeah.
Yeah,
Right.
I think this should be
Okay.
within the support.
Okay. Thank you. Yeah.
Yes, I should clarify this. Yeah, it should be almost everywhere on the support. Yeah, and yeah, so for this um, for this concept, the basic idea is that we can write an approximate identity using a finite sum of basically we try to make approximate identity using a neural network, a single hidden neural network. And so it's possible to approximate other function by using this approximate as a modifier. So it's a useful technique um, in approximation that we can use this as a using the convolution. And so we have an approximate to other function as well. Um, the other two assumption why we need this thing, or maybe why we need the convex and kind of smooth boundary. We do need to ensure that there's some regularity on the Monge-Ampere equation later on, to meet some to have a certain degree of regularity. And so this based on the work of Cavallari on CPAM of 92, or maybe on Anomat in 96. And so this becomes standard when we usually dealing with Monge-Ampere equation. So the assumption is also really standard and it's not too strong. It also like only need on the initial and the terminal density function. So it's kind of reasonable compared to we have to assume on the vector field where we actually don't have any information. And then based on the above assumption, the above assumption, we can actually construct a neural network, a neural network in here with a mass control, so that the solution, the theorem mu t in here will approximate the exact solution of a certain exact transport equation. Of course, in a sense, we also need to construct this explicitly, because as I mentioned, um, the vector field in the exact equation actually not unique. So we will use Monge-Ampere to construct this vector field as well. And so when we use Monge-Ampere to construct this thing, and we use another Monge-Ampere to construct vector field, and so they will approximate in using the stability result of Monge-Ampere. Now,
Okay. Yeah.
for
Can I
the
ask?
error estimate, we use
Yeah.
a bounded Lipschitz distance. This is the definition.
Sorry,
So
Nhật.
yes,
Yeah, yeah. Can I ask? So can you, yeah, so I understand that you have F and G are given with the density
yes,
satisfying your assumptions. Um, and you are doing some sort of inverse problem here, but can you specify? So F and G are known, capital T is known. You are constructing the vector field by using the neural network, and the control is a zeta T is also the control.
yes, yes.
When you say, write that it's approximate the transport or the Fokker-Planck equation below, what is known and what is not known? I mean, I'm a little bit confused. Uh,
Actually, in
ET and yeah.
when we construct this thing, only the form is this form kind of
Mm-hmm.
known, and we have to find W, A, B, and zeta,
Mm-hmm.
and only actually only this thing is known, F and G is known, and so we
Mm-hmm.
actually have to construct a lot. We have to construct both this thing, these two vector field. We
Okay.
have to construct the approximation here along with all the neural network coefficient with the zeta. So
Okay. So
yeah,
the
actually we have to construct a lot of things, and we have to ensure they converge to each other.
but what do you mean by converge to each other? Because the second equation you said that is also not known, right?
Yes, yes.
Yeah.
We have to specify what structure we have for the vector fields here.
Okay. Okay.
Otherwise,
Yeah.
we cannot ensure that this actually converges to this thing.
Right.
Um,
So
yeah,
that
because
means that the
they are
second
not unique.
equation you have
Yes.
information.
Yes. The information we have should coming from F and G, and it should have some unique structure based on the Monge-Ampere equation.
Okay.
But we have to specify it, otherwise we cannot say how this converts to this thing because
Okay. Okay.
it's not
Yeah.
unique. Yes.
Yeah. So you can
So
say
that
gonna
that
say it
that also
later.
one of the challenges when we try to construct as well, because this is not unique and it's very hard because if it's not unique, usually other method cannot converse in any sense because it's not unique. And so the
Okay.
construction in here is very important that we have to specify it clearly.
Yeah. Go ahead,
Um,
please. Thank you.
yes, thank for the question. Um, and yeah, and what we want to obtain is that the solution will converge to the exact solution. And so in a sense, of course, the two ends also converge to each other. Um, and about it, Lipschitz distance, it's actually a metric for the weak conversion of measure. So this is the metric for the weak conversion. Um, Usually this also appear when you study for optimal transport with Washington distance. So in a way, so this is not that people already study it before the Washington distance. It's just nowadays Washington distance is more popular, but we will use the distance. It for now it better because the condition here is kind of working for us. Although if we can do with other distance, and it would be nice, but for now we do this distance. It's still a metric for weak conversion, so it's quite sufficient to say that this converts quickly to um, this convert quickly to the solution. And so this is how we try to construct. As I mentioned, we 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 will try to using an optimal transport, and we form a dual problem. And so the thing here, we have F and G, and then we try to use the dual problem. We have a, a, a solution for dual problem from the optimal transport problem, and then we might have some smooth approximation using modifier, and then we go backward with a dual problem. So we have approximation for F and G. And for the dual problem, we can use Monge-Ampere solving it, and then we use the Monge-Ampere to construct the specific vector field in here. And then we also do the same. We have the Monge-Ampere solution in here, and we construct the vector field in here. And then after we have these two vector fields, we use the idea of neutral approximate identity that I mentioned earlier. So it also approximate identity, and then we can use another modifier on this thing to get the neural network. And so so that's the structure of the idea. The first thing I try to do is the Monge-Ampere. How we suppose that we have these two. How we actually do with the Monge-Ampere is just a reminder. So the Monge-Ampere equation is defined as follows. So we have V, and the determinant of the Hessian it should be equal to U. In the exact form should be like this. We use the weak form, so it have it have this form. So the existence of the solution already in by Marken in 95, and then we have a lot of solvers. Usually, what we look at usually in by Benamu and Carter. Um, I in both papers, the author like will actually introduce two different solvers, so we can actually have many solvers to choose from. In here, we just assume that we might have we can get a solution, maybe or maybe even only need an approximate solution in here, and that's enough for us because later on we only need an approximation. And so so this is the we assume that we have the Monge-Ampere, and now assume that we have the Monge-Ampere. So this should be the structure. we have a t in here, usually a point transport. We have a point from x, try to transport through to um, the gradient of the Monge-Ampere equation with at x, and so we kind of transfer it in a line, and then this will define the vector field. This will define the vector field, and so for the homogeneous transport where you not consider the mass yet, so this should be the form of the equation. So for unbalanced transport, you will add the mass in, and you will have a structure from the Monge-Ampere equation. In here, of course, as I mentioned, this is homogeneous, so this is still balanced transport where the total mass of U and V should be the same. We will come back with the inhomogeneous transport, but now um, what we need now is 2K, right? Because we have the idea that we need to do some Monge-Ampere in here, and to do that, to have this equation, the total mass of U and V still need to be the same. So we need to find some K in here correspond to F and G. And so what we do is we form an optimal transport problem, and then we form a dual problem to that optimal transport. And because we have optimal transport and dual transport, dual problem, it will form an identity to for us between K and F. So the first thing is the optimal transport. Of course, we have some cos C. This is the cos function, and we want to transport with this cos, but we will put some penalization on we put some penalization on the marginal. So at F and G, we can put some kind of difference in here with a square. So this usually appear with a G square test. So it also quite popular. Other author usually use the KL, the Kullback-Leibler divergence. In here we use the G square. Um, there are some reason for that, because in here we need a continuum setting, and so the G square usually provide a strong convexity, and so we decide to use the G square test in here, um, in order to ensure strong convexity. We also add this is from Sinkhorn. Usually they also add some penalization in, and we design another square from L2, and this ensure the strong complexity of the whole term. And so the minimization should with strong complexity should not be difficult. It makes the process easier to deal with. Um, and so based on this problem, this is the minimization problem. One thing we also ensure that we have a lower bound for the transport density in here. So this is the transport density, and so we want to ensure that this have a lower bound. The idea is that it's very similar to why we need a lower bound for F and G. It have to avoid the point zero to ensure some regularity when we construct the Monge-Ampere. Um, and so we do need this lower bound, but we can choose this a positive number, which is very more. And then based on this formulation of the minimization problem, we of course this is a little bit technical when we try to derive the dual function, but we will derive the dual function, and then when we combine them together, we have a dual minimization problem. And so why we need to consider optimal transport and dual problem is because they will provide um, multiple identities where we can work on with F and G. So instead of F and G, when we use Kx and Ky, it have this identity with the dual solution. So using this, we can actually finish this step. We can how to find kx, ky, and if we have approximation, we can also find the approximation for f and g in here. So the idea is that the optimal transport and the dual problem um, will give you identities where you can compute them. So so now um, it's come to whether we can solve the optimal transport problem or not. Because after we can solve it, then we have f and g, then we can construct kx and ky. And so that is this step here. We can finish this step here, and the most approximation is that a modifier. So we actually finish this step as well. And so to solve the problem, we actually have to make the whole algorithm to solve the dual problem and the optimal transport problem. We have to uh, introduce a new algorithm based on the decrease algorithm. So the algorithm we use are actually inspired by by the paper with four authors in 2022. And so the paper actually about gradient. The Sinkhorn-inspired with, as I mentioned, it comes from the penalization that we add to the optimal transport problem here, and maybe and also in here as well. So that the basic idea for the Sinkhorn and all the variation of Sinkhorn algorithm, they also add some, maybe they will add some different penalization. We use the L2, as I mentioned, we want to ensure the strong convexity with to make the minimization become more stable. And then the thing that it have the name gradient base because we will have the gradient descent inside the algorithm. So we know it is strong convexity. So gradient descent is quite a popular choice and quite easier to choice to do it. We do try to make some simple numerical tests, and I will try to show it later after we finish all the thing. And so how this um, how this algorithm look like. The first thing with the gradient, we can choose we want to find some conversion rate from 0 to 1. So we write at q over q plus 1. And then we will have some kind of technical estimation for the gradient descent. So we will use a number defined like this, where this is the lower bound for f and g. And so we choose this at this. We use this formula. It actually signifies some estimates, and then later on. Finally, we can choose the Q here. We can find the Q here. So that the Q and S should be the Lipschitz constant of the dual for functional. We have this functional, and actually we will find the radian of this functional. And then we actually prove that it is Lipschitz functional, and so we will try to match choose Q in here, so that this is correspond to the Lipschitz constant, and then we will get the conversion rate R in here, and then the gradient essence step you can see in here. The other two step is the gradient, where we try to choose so that we have the minimal and maximal in a function that is coming from the dual problem in here. So it will come some gradient, and then we try to choose the minimize and maximize point in there. So it's a little bit technical why we have why it had this form, but it's basically coming from this dual formulation, and then we try to make the gradient zero. Yeah, of course the y will have the same update. In here the output should be the zero in here. The output of our algorithm will be the zero in here, and also y zero if we also update it. And so we have the dual. When it come out, it should be approximate these two function. It should approach these two function. And so after you have these two functions, you have f and g, and then of course you have kx and ky. And so that finished how can we find k in here. And now after we have k, as I mentioned, we use some it's a modifier, not modifier. Yeah, and then we use some modifier to make a smooth approximation. And then with the smooth approximation, we take k in here, and so we can define the approximate f and g. And so this is the error estimate that we can come that we have. So this is the conversion rate that we mentioned earlier. So for gradient descent, it exponentially decays, so it's fine here. And then we have the epsilon zero that is coming from the error of the modifier. So the total error estimate is just the total of the algorithm plus the error from the modifier. And so we have the approximation. And now with the approximation, we now solve the Monge-Ampere equation as mentioned earlier. We have T and C that is in here. And this is the mass control that we come up with. We can put the mass control here. Also a little bit technical because when we compute it should match. It should push the F to C at desire. So yeah, this part is a little bit technical. This part only come up from the old technique where they try to use the Monge-Ampere for the balance transport. So it's only well known for balance case. For unbalanced, so this thing is what we come up with. And it in our paper we actually prove that this actually work. And so now we have kind of a transport. We have a transport. And then we want to do a neural network at least for the flow control in here. We can keep this mass control. And then as I mentioned, we have um, the definition of using the Monge-Ampere equation. We construct this thing using Monge-Ampere equation. And then we might need to take another modifier to make this smooth enough. And then we will take another modifier from the definition of neural approximate identity. And then we take the convolution. So now using the convolution, it's just like the integration. So instead of using integration, we use the quadrature rule. We put into multiple points, and then we can put it in at a finite sum. And so this will give us a structure of neural networks using only the finite sum, and then so we can merge them together to make a coefficient for the so what we get is the coefficient in this case. So what we only need to do in this step is that we only need to compute. We merge them together, and then renumbering. So we have some number in here. We can renumbering into 1 to n. So it's just the final step is just like renumbering and merge them together. one thing in here is that this is only one dimensional. So we do need some other tools to make it from when we have multiple dimension, we want to make it into a one dimension problem. And so actually before us, so Chu and Sinli already success the Drix functions in 92. So that after they have the smooth they have the smooth vector field in here, they can approximate it by polynomials, and then polynomials they can solve a linear system to write the polynomial into the finite sum of this form. So this is called the Dirichlet polynomial, and this is the concept of Dirichlet function. They define here, and so after we have the Dirichlet polynomial, so we can consider this is a polynomial in one dimension.
Nhật, can you wrap up
Yes.
in 1 minute?
Oh yes. I think yeah. So the idea is that after we use the Dirichlet polynomial, we have a neural network using this form for higher dimension as well. So we can solve it for many. And the final thing is the error estimate, where we we have the error estimate from the dual problem that I mentioned earlier. We have the epsilon 1 from the construction of neural approximation. We have a lot of approximation here, but let's say we have error epsilon 1, and then we have the epsilon 2 between the solution of Monge-Ampere equation, because we have two Monge-Ampere equation as I showed earlier. And so what we show that the distance, the bounded Lipschitz distance actually bounded by this error, error with some constant in here, but it shows that we actually have a small, arbitrarily small distance, so it actually converts in weak conversion. Yeah, this usually additional thing that I want to show is that some numerical tests where we put for example, it's here is C is constant. So the mass the transport mass supposed to be concentrated on where the mass have the most. For example, in here, X is bigger than the mass is bigger, Y is smaller than the mass is bigger. So it's concentrated at Y near zero, and X at one in here, and so it reduced along the axis. We also try to do the other test where we have a constant density mass, and then the C, this is the formula of a circle. So when we actually running it, you can see it should concentrate it near the center because it's the cheapest way to transport thing. So this also it's a simple example, but it's verified that we have a correct algorithm to work on. Yeah, we also testing on another thing, and it's worked quite well. In here, we only need like around 20 iteration to have a stable. We can only run 50, and then it quite already very stable. And so our algorithm work quite well. And so that wrap the thing wrapping up. Thank you everyone for your attention.
Thank you. Thanks a lot. So are there some quick questions for Nhật before we end our formal discussions, and then we can switch to the informal one? Any quick question for Nhật, please?
I have a bunch of questions, but I'm not sure if maybe they're quick because maybe I
Yes,
have some
please.
naive questions. Maybe
Yes,
yeah,
you can ask question.
it's really interesting. I think it's really nice, but I'm not sure I understand. There are so many things I don't quite understand. So you told us like for the unbalanced transport equation, there's no uniqueness, but somehow
Oh,
you
the non-uniqueness in
uh-huh.
here, right?
Right, but somehow at the end of the day, you have the unique. the unique solution in your algorithm. So I'm wondering, is it coming
Oh,
from
yes.
your optimization formulation for the dual equation because it's a very special formulation? I'm
Yes,
wondering.
yes, because yes, the uniqueness is in here. We might have a different vector field C and zeta in here to
Mhm.
have the transport from F to Z. But in here we have to specify that uh, the construction should follow this form, and we're not going out of this form. And so because we only have the specified form, so it's unique in the sense that we have to define it in this way. But for other form, we cannot be sure that if other vector field can fulfill the task to transport F to Z. And
I
so it's
see.
only unique in the sense that we have to fix the structure in this form.
In
Otherwise,
this,
yes.
can you go back to page 22? Oh, 21, sorry. I'm sorry.
Uh,
20.
yeah,
Yes,
it is
no, 18, please. Sorry. Can you go to page 18, please?
18.
A18.
18, yes. Thank you.
Yeah.
Yes, so I was wondering, is the uniqueness coming from this minimization problem or this is somehow standard or how
Yes, yes. One thing in here, for the minimization problem, um, actually it not, it might be unique, um, but only up until if we fix this condition, we have to
I
fix the
see,
condition as well.
I see. And
It will exist some solution that less than the certain number from F and G. Otherwise, they will just take the max in here, and but so it's not unique in some sense because like if it greater than certain level, um,
I see.
they kind
So
of ignore it.
so am I
Yeah.
right? So the minimization problem holds in general, but the uniqueness is coming from the special form of
Yes,
your
yes.
KX KI.
Yeah.
I
It's
see.
very coming from the spectral form that we define. For example, in here we have to we after we have this equality, and then we enforce this thing, so it have a unique solution that satisfy this condition, unique up until almost everywhere with Lebesgue measure. And so kind of have a unique case storm here, and then we have this equality to define kx and ky, so it's also unique almost everywhere. And yes, and then the uniqueness also come from the structure that we have to enforce this structure. So a lot of stuff that we have to enforce to ensure that we have a unique structure to converse to. Otherwise, as I mentioned, um, the dynamics, they are not unique. So um, if we don't specify the structure like this, then we cannot say for sure how the conversion happen between the two dynamics.
Thank you so
So
much.
yeah.
Okay.
Yes, thank
Thank
you
you,
for the
Nhật.
question. Yeah.
Okay, so let's stop our formal discussion here. So let's thank Nhật again for a very interesting talk.
Thank you, everyone.
Thank you.